I'm Brett Gildersleeve, and as a product manager at Meta, my goal is to help developers use the power of audio to create a realistic sense of presence for people when they're in virtual environments. Immersive audio creates dimensionality, a sense of place, and even identity for users. So today, my colleague Henry from the sound design team and I will provide an overview of spatial audio and room acoustics and help you understand the role that these can play as you create immersive VR experiences. We'll also provide real-world examples of these features in action. Finally, we'll show you how easy it is to start building amazing audio experiences in your next app using Audio SDK, which will launch as part of the Presence platform soon. Presence platform is the collection of SDKs and APIs from Meta that provides developers with AI, machine perception, graphics, and audio capabilities to build immersive experiences that blend the physical and virtual worlds and help people connect with each other. When paired with MetaQuest devices, Presence Platform empowers developers to innovate and unlock new use cases with mixed reality, social presence, and interactions. What does it mean to hear sound in 3 dimensions? In real life, we don't just hear sound between left and right. We hear it behind us, in front of us, below us, and above us. Spatial audio is a big component of creating a similar experience in virtual reality. In order to understand the role spatial audio should play in the virtual world, we first have to think about how people perceive sound in the physical world. For starters, how do we understand where a sound is coming from using our ears alone? When sound waves approach the human ear in the real world, they hit each of our eardrums at slightly different times. First in the ear that's closer to the source of the sound, and then slightly later in the ear that's further away. Sound waves also get quieter with distance, so the sound is louder in the ear that's closer to the source, and a bit quieter in the ear that's farther away. These are some of the clues that the brain uses to figure out where a sound is coming from. On their own, though, these subtle differences in timing and level don't provide quite enough information. For example, imagine placing a sound source either at position A in front of us or position B behind us. Because these distances are equal, the brain can't make a distinction between the two. So, how do we figure this out? Well, for one thing, our heads are never really stationary. We're constantly making small, subtle movements. You can see in this diagram that as the person rotates their head slightly, the distances between the sound sources in each ear will change. The brain picks up on these tiny differences and helps us distinguish between front and back. In the same way, these micro movements can help us determine if a sound is coming from above us or below us. Beyond these differences in time and level at each ear, another major contributor to how we hear in the physical world is the way that sound waves interact with our bodies, particularly our outer ears. Sounds reflect off of us and bend around us, and this changes the way that they sound when they finally arrive at our eardrums. This is known as the head-related transfer function, or HRTF. The brain uses this combination of cues resulting from the HRTF, as well as the differences in time and level between the ears that we discussed earlier, to figure out exactly where a sound is coming from. In other words, human hearing is complicated. And in order to help people feel immersed in VR, they really need to hear things approximately like they do in the physical world. But the standard game engines we commonly use to build VR applications don't usually take all of these subtleties around spatial audio into account. That's because these game engines weren't specifically designed to build VR applications. They're usually more general purpose, allowing for games that run across a variety of devices, including PC, mobile, or consoles, and with speakers that are fixed in position and don't track the user's head movements. Now, these game engines actually have a lot of great audio features. They allow designers to place sound emitters at any point in 3D space, and when those sounds play, They're panned between the left and right speaker to help give the player a sense of left-right positioning, as well as distance. But this lacks some of the subtleties that we hear in the real world. And as a result, it won't do a great job in tricking your brain into feeling immersed in VR. The real power of VR headsets when it comes to unlocking convincing spatial audio is head tracking. We can use the position and orientation of a person's head to automatically adjust the time and level in each ear independently for each sound that is played back, as well as applying the HRTF. Together, this allows people to hear things in the virtual world in the same way that they hear them in the physical world. If you've ever listened to an album in mono and then experienced it again in stereo, you've probably recognized the qualitative difference that extra dimension creates, and noticed details that you missed in the mono version. Spatial audio is the next evolution of this concept. Even though a VR headset might have a limited field of view, the auditory field of listening is a full 360 degrees. This gives the user peripheral awareness and allows them to understand where things are, even if they can't see them. This also makes the audio mix less cluttered, allowing people to hear more detail from individual sound sources, even when many sounds are playing all at once. If we look at this example scene, where we have sound sources above us in red, behind and below us in blue, and off to the side of us in green, if we build the scene in VR without spatial audio, everything will sound like it's roughly on the same plane, aligned with the user's head, as pictured here on the right. Without spatial audio, our sense of localization is relatively poor, preventing us from accurately judging the location of each source in 3D space. The sense of externalization, when using non-spatial audio in VR, is also poor, meaning that rather than sounds seeming to come from out in the environment, they tend to sound more like they're coming from headphones placed over our ears. Overall, without spatial audio, there's a mismatch between our eyes and our ears that just makes things feel less real. So, our ears can tell us where sounds are coming from thanks to spatial audio, but that's not all they can do. They can also tell us a lot about the environment that we're in. What kind of space are we in? An expansive cave? An open field? A padded cell? How big is it? What materials is it made of? Our ears can tell us all of this based on room acoustics. In the physical world, sound waves spread out from a source similar to how ripples spread across the surface of a swimming pool. While the waves that take a direct path to our ears are the ones we hear most prominently, countless others reflect off of the walls, ceilings, and floors and other objects in the room before they reach our ears. We call the waves that arrive first the direct sound, since they travel in a direct path to our ears. Those that arrive shortly thereafter, after bouncing off one or two nearby surfaces, are called early reflections. And the waves that bounce around many times before they reach our ears are called late reverberation. The materials of the walls, ceilings, and floor will reflect or absorb sound waves in different ways, which can change how these reflections sound to us. The brain is incredibly good at taking in all of this information and giving us an understanding of the physical space we're in, including the size, shape, and material properties of it. Think about it. If you close your eyes and clap your hands, you'll easily be able to tell if you're in a big carpeted living room or a small concrete bunker. So, how does this work in game engines? Well, similarly to spatial audio, game engines don't apply room acoustics by default. When you hear a sound in a game engine, the default behavior is to just play the direct sound. This gives you a feeling that you're floating in space. You have no sense of the environment that you're in. Because of this, adding artificial reverb to sounds has become pretty common practice in game development. But just applying any old reverb often leads to a mismatch between the way a room sounds and the way it looks. When this happens, especially in VR, people will get the sense that something is off. Using an analogy from the graphics world, we might get a similar feeling when we see shadows that don't correctly match the lighting in a scene. Using the wrong reverb can be immersion breaking, especially in VR apps. For example, a person might see a large room around them, but it still sounds like a small closet. There's actually a name for this in research literature: the room divergence effect. As you can see in this excerpt from a research paper on this subject, room divergence causes a collapse in the plausibility of the overall auditory scene. For the end user, this effectively means that it can break their suspension of disbelief. Luckily, we provide tools that will help you easily create room acoustics that correctly match virtual spaces. And this really makes virtual environments much more believable because our eyes and our ears won't be contradicting each other. Immersion is one of the goals of virtual reality, and the combination of spatial audio and room acoustics are vital in achieving this goal. When these are done right, we truly feel sonically teleported into the worlds we've created, rather than just observing them through a screen. With that in mind, to talk about some real-world examples of how we use these features in our own VR experiences, as well as help you get started with building your own, let me introduce Henry Halverson.
So Brett has covered a lot of spatial audio concepts and terminology. Now, how do we apply these in practice and really pull people into the virtual worlds we create? Hi, I'm Henry Halverson. As a sound designer at Meta for the past 3 years, I've used spatial audio tools to build high-fidelity audio experiences for our users. And I hope to share the benefit spatial audio has brought to our applications, as well as inspire you to discover and use these integrated audio tools in your own development processes. Highly immersive spatial audio will help you realize the full potential of your ideas when building apps with the Presence platform. You know, this isn't new territory for our team. We've created and refined spatial audio tools for many years on the Rift and Quest platforms. And now we plan to offer these same tools here in the Presence platform, along with various new features and improvements. Here at Meta, we've already implemented spatial audio and room acoustics in a number of different VR applications. Our app Horizon Workrooms is an excellent example. Workrooms is a VR space for teams to connect, collaborate, and develop ideas together. And audio helps make this experience feel real, allowing team members to speak with one another naturally, just as they would in person. In practice, this means if several team members are sitting around a table with you, you'll hear their voices all coming from the correct locations. This spatial separation is something we are inherently familiar with as humans, and allows our brain to more easily distinguish between voices. Workrooms also leverages audio directionality. So if someone is speaking towards you, they will sound clear. And if someone turns their head, their voice will be intelligible, but perceived as a bit quieter and less distinct, just as you would expect in the real world. Adding room acoustics to Workrooms helped make the environment feel more inviting. The room acoustics in Workrooms has been set up to mimic the geometry of the space and fine-tuned to make each space feel right. When these audio features are used well, people can make sense of a virtual space, even with their eyes closed. Spatial audio has been shown to make conversations more memorable and can improve comprehension. So let's jump in now with Brett and take a look at these features in action.
Hey, Henry, welcome to Workrooms. So, as we discussed earlier, spatial audio helps to localize my voice so it sounds like it's coming from here where I'm sitting. If you were to say, look out that window at the beautiful scenery, you should hear my voice coming from your left and behind you, kind of over your shoulder, just as you'd expect. Also, the room acoustics in here are set up to match the size and shape of this space, making it sound more natural. My voice is also directional, so if I were to say turn around and look at the whiteboard, you should hear my voice is a little bit muffled as I'm facing away from you, and it's more clear as I face back towards you.
Workrooms is an excellent example of spatial audio within a social context. These same audio implementation techniques will bring to life any experience you create when used in conjunction with other tools in the Presence platform. We encourage you to use spatial audio in mixed reality experiences to fill the space around you with sound. Use these audio tools with the Interaction SDK and create hands-first experiences without controllers that use audio to provide an additional dimension of feedback to help support interactions with virtual objects. Our recent Interaction SDK demo firsthand is another example of the impact immersive audio can have on a project. Let's listen to the audio in this experience. Listen to how the sounds of ambient objects fill the space and create a sense of presence. I really love how the sound design in this demo gives the player information about what they should do next. And when the player touches something, they learn more about it through how it sounds. Now, let's talk about how you can get started creating immersive audio for your app with the Audio SDK. Our goal with offering spatial audio in the Presence platform is to make integration quick, accessible, and intuitive. We have built in enough flexibility for you to craft the audio experience that feels right, while keeping things easy to use. If you are a developer with limited experience in audio, you'll find the SDK contains several easy-to-understand components, which integrate with and expand the functionality of Unity's native audio engine. If you are an experienced audio programmer or a sound designer in search of a powerful spatial audio or acoustic solution for your team's upcoming project, you'll be able to dive deeper and uncover the true potential of the Audio SDK. We've added several new audio features and will continue to expand the feature set in the future with more advanced control over spatialization and acoustics. We plan to provide SDKs that work with Unity and Unreal game engines, as well as audio middleware providers Wwise and Fmod. You can expect the Unity Audio SDK later this year, and then support for Unreal Engine, Wwise, and Fmod will follow after that. So keep an eye out on our Presence platform website, where we'll launch a public experimental release of the Audio SDK later this year. And check out other sessions on the Presence platform at Connect. We hope you feel inspired to leverage the power of Audio SDK to create a truly immersive experience.